But they know a lot better.
I mean,
Clapping could make that.
clapping. Okay, time to start again. It's my pleasure to introduce Jurij Volčič.
Yeah, so based on some joint work with Igor during this morning, so Scott and Victor are gonna come up. Now, as you heard in Igor's and Scott's talk, right, we like to look at non-commutative polynomials and non-commutative rational functions as functions on matrices, well, more precisely on tuples of matrices of all possible sizes, right? And in the alternate talk, Victor is going to tell you a bit more general picture of how, I mean, we have a notion of a non-commutative function, so not just polynomial rational. No. So anyway, our functions live on all matrices of all possible sizes, right? So that's kind of our geometric space, if you want. Now, if we want to have at least some kind of a baby algebraic geometry going on, we should know what's a hypersurface in this setting. What should be a hypersurface? And today I'm going to talk about that. If you give me a non-commutative polynomial and I look at all the matrix tuples where this polynomial is singular, that kind of, in some sense, gives us the appropriate geometric image. So first we're gonna, and I mean, what do we want to have from hypersurfaces? Like in classical algebraic geometry, we want to have some Nullstellensatz. Two polynomials give me the same hypersurface. What's the relation between those two polynomials? First we'll look at some motivation and also like different versions of what the zero set should be. And then we're gonna first we're gonna give some answer for monic for pencils, for linear pencils, then some theoretical tools, and then in the end we're gonna get a nice general statement, and of course there's gonna be some open questions that we still don't know. Okay, so throughout the talk, I'm gonna write this K to be field of characteristic 0. At some point, it's gonna become algebraically close. So I always just think of complex numbers, to be honest. So x1 to xz, these are gonna be freely non-commuting variables, and we're gonna talk about elements of free algebra, or sometimes you're gonna take matrices over elements of free algebra. So these are gonna be matrix-valued NC polynomials. I'm just gonna call them NC polynomials. So what's an element? Well, an element, it's a sum. You can think of it like, oh, it's a sum of matrix coefficients and words in x1 to xd. Or you can think of it, well, that's a matrix, and now that's a delta times delta matrix, and each entry is a NC polynomial. It's an element of a free algebra. And so we can evaluate them on matrices, on matrix tuples. Namely, well, I take a tuple x1 to xd, I just substitute each of the small x1s with a capital X1 and so on. Wherever I see a constant, I replace it with the identity matrix, and then I get, so if f was a delta times delta, NC polynomial, what I get when I plug in n times n matrices, I get delta matrices inside delta. So this tensor product here is a supercomplete thing, it's just a Kronecker product of matrices. I know it has special interest in linear ones, so in linear polynomials, and they have a special name, we call them linear matrix pencils. So delta things out, it's linear. And especially when it comes to positivity and convexity and whatnot, we like to set up the constant term to be identity matrix, and in this case we say that pencil is monic. Okay, so now let's first look at a few candidates for a zero set or Nancy polynomial. So let's pick two polynomial set in G type. And now the first one is the hard zero set, right? The obvious choice. So I'm going to just look at all tuples of matrices of all possible sizes such that f of x is really 0. So this is called free zero set or NC zero set. And here we have some result, pretty old, 60s, 70s, by Amitsur. So if I fix an n here, then I have this kind of a Nullstellensatz result. So if every zero of f is a zero of G, then G to some power is going to line the ideal generated by F. And maybe I need to add some polynomial that's constantly 0 on n times n matrices. So this PI n stands for polynomial identities for n times n matrices. Now this is for a fixed n, right? And then of course, as I said, in our setting we would like to get kind of a dimension independent result. So one think, well, okay, if I know that that happens for every n, can I kind of glue these statements together to get an independent statement? And the answer is no. And this, I mean, roughly speaking, that's a consequence of the fact that not every algebra has finite dimensional representations, or doesn't have enough of them. So in general, that we can't really glue this into a good statement. Sometimes it works, so that there's something that there's good answers for rationally resolvable ideal and for homogeneous ideal. So if this F would be homogeneous. Okay, in general, we don't have great answer. A different way of thinking about zeros would be the following. Well, I take a polynomial and now I'm going to look at all the pairs of matrix point and a vector such that F at that point times that vector is going to be 0. So kind of you give a 0 with the direction of the sphere, right? So this is called a direct attention 0 set, and so this was this appears in Scott's and Bill's paper, and it's due to Bergman. So Bergman proved that in this case you also have like a nice Nullstellensatz result. So if every directed 0 of F is a directed 0 of G, then you know that F is a right factor of G. And okay, I wrote one implication. It's actually in both directions, right? In one direction, the other direction, it's kind of a issue. Okay, so these are two possibilities, and what we're going to talk about today is the third one. So I'm gonna think of zeros of F as tuples of matrices where F is not invertible. In other words, determinant of F of X. So that's going to be the object, our geometric object for today. So in general, not just for ANSI polynomials, but for matrices of ANSI polynomials, we define its free locus, or free singularity locus, as just as, so we're going to use this notation, over all sizes of matrices, all x's such that determinant of F at X is 0. Okay, so what are the first properties of this set? So first of all, I mean for each, what's that? That's actually, well, it's a disjoint union of what? Of these things. Well, these are determinantal hypersurfaces, right? And it's a hypersurface, it's given by one equation. Determinantal given by determinant. It's clearly invariant under some action, right? I mean, if I take an x where f of x is singular, and then I simultaneously change the basis on all matrices in X, so I again get something where f is singular. So these hypersurfaces, they are preserved under basis changing. And then some easy observations, right? I mean, if I have so this was low, so this was on one particular level for each fixed n, I have this invariance, but then also these levels that kind of are related, right? I mean, if I have on some level, if I have this point x where f is singular, then I mean from this point I can build up plenty of other points where f is singular. And also, I mean, if I have a product of two polynomials, then the free locus of the product is just the union of the loci given by those two polynomials. For example, if they appear on a diagonal, this is a matrix. And so they did this, especially this property here, and this, I mean, this kind of gives you a feeling, oh, that kind of indicates like a hypersurface in some sense, but then you also have this kind of a slightly maybe surprising property. It's easy to see that when you think about it, but it's just kind of surprising. So that if I have an intersection of free loci and that lies in another free locus, then one of them is co-contained. So maybe that's not something that one would really expect from hypersurfaces. So what I want to answer today is the following. So if you give me two polynomials, what does it mean that singularities of F are contained in singularities of G? It's like there should be some kind of a Nullstellensatz result. And of course, I mean, if I mean this is a family of these hypersurfaces. I mean, hypersurfaces, they might have components or not. So, I mean, what can I say of the components of the free locus? How does that reflect the structure of that? So why do we care about this particular setup, right? I said that I mentioned that there are kind of three options how to look at zero set of a polynomial. Well, all of them are good in some sense, right? It depends what you want to do. Why we care about this singularity setup is the following. So Igor and Scott talked about polynomial inequalities, right? So about three semi-algebraic sets. So you take a polynomial and you look at all the sets, all the points x where f of x is positive, same definite. Now, roughly speaking, I mean, okay, this is a set where f of x is positive, definite or same definite. When you go to the border, what happens? I mean, if you go to the border of this set, well, at least one of the eigenvalues needs to become 0, right? So f of x becomes singular. So these hypersurfaces, they are more or less the risky closures of the boundaries of this set, right? So if you want to say something about this positivity set, it often suffices that you know some stuff about the boundary set. So so the free loci, they appeared in various ways in what we did. So relating to either convexity or, for example, also we talked about non-commutative rational functions a few times in the last few days. Free loci are more or less exactly the complements of the domains, right? So sometimes you want to say something about the domain of an n rational function. You're actually talking about something about a free locus. Maybe what I'm going to talk most about today is that free loci are kind of a geometric counterparts to the factorization in free algebra. And there are some other applications related to smooth points on free loci, how that affects our knowledge about bioanalytic nets between free spectra, and so that's what Scott was talking about, convexotonic nets and so on, and we can talk. There were some results related to stability. Now, at least in three of these cases, kind of the only the loci to talk about convexity and rational functions and these ones. So here we actually one just cares about free loci of pencils, so affine polynomials. That's why we're gonna address this situation first. So what can I say about loci of pencils? And first we're going to restrict to monic pencil. Later on I'm going to explain why monic situation is much easier than the other one. So I take a monic pencil, right? So identity plus sum of aj, xj, and let me by curly a, let this be the matrix subalgebra generated by these matrices. Okay, so it's some finite dimensional algebra. Let red a be its radical. What do we mean by radical? Well, we're in finite dimensions, so it's more or less all the radicals coincide, right? Is that Jacobson radical or largest impotent ideal or whatnot? And then you have this kind of if you want Nullstellensatz, that's kind of a result. If you give me two pencils, what does it mean that singularities of one are containing singularities of the other one? Well, that means that if I look at the map that maps coefficients of the second pencil to the coefficients of the first pencil, it's going to induce a k-algebra isomorphism between these algebras. Well, not exactly between B and A, but with this quotient algebras, B modular radical to A modular radical. So why is that actually good? Well, I mean, now we can kind of, if you give me a pencil, we can actually check now this inclusion of free loci, because that, I mean, these algebras here, they are not too abstract. I mean, these are algebras given by generated by some matrices, and we can work with these algebras. So, for example, there are some good probabilistic algorithms to determine the structure of it. So, kind of finding the radical is the most technical bit, but even that we can actually compute two algebras that is more. And when we're looking here, so how does the geometry here capture some multiplicativity happening here between these two algebras? The following is kind of the core of it. So just call it algebraization trick. It's actually just sure complement thing. If I take this matrix, so determinant of, well, identity plus a1, x1, a2, x2, and then the third coefficient is going to be the product of these two, well, the fact that I kind of want to say something about the product of the coefficients, which comes here with when I'm talking about this matrix algebra, I can encode that in twice the size matrices and just still talk about pencil in A1, A2. So that's kind of that's the way how this multiplicativity here can be encoded in free loci, or vice versa. It's gonna show up a few more times. Okay, so that's for monic pencils. That's kind of already a nice answer. Now we want to say something about more general matrices of polynomials. So we need to say something about factorization. How does factorization work in free algebra? And first, we usually don't talk about factorizations for all possible matrices of polynomial. There are ones that we just don't want to deal with, and that's the non-full ones. Now, what does being full means? That, well, a matrix is full if it can't be factored as f1, f2, or so this was delta times delta. Now f1 is delta times epsilon, where epsilon is smaller than delta, and f2 is epsilon times delta. So it's kind of a, we don't want to deal with matrices that factor like something tall, something long. Why is that? I mean, if I have matrix like that, it's always going to be, I mean, it's never going to be invertible, right? I mean, because if whatever I'm going to plug in this, I mean, this is going to have some kernel and so on. So in this case, the free locus of such a thing would be trivial all the time, so it's kind of uninteresting. And also from factorization point of view, it's not, those are not well behaved. And actually that's exactly what happens, not just that every matrix that factors like that, it's always singular, it's also the other way around. If some matrix of polynomials, it's always singular, it actually factors like that. So that's basically back to Matricial and Cohn, right? Being full means that at least at some point f of x is going to be invertible. And furthermore, I mean, f invertible, when I say f invertible, meaning f invertible inside this string, so that I also have a polynomial inverse, that exactly corresponds to well, determinant of f of x is non-zero for all x. So if you want to think just about the case delta equals 1, full just means that it's a non-zero polynomial. Invertible just means it's a constant polynomial. That's in the scalar case in delta equals 1. And now we can talk about, well, I want to talk about factorization. I should say, well, what's here an irreducible polynomial? Well, we assume that it's full and non-invertible, so to exclude these cases, and then being irreducible, or sometimes these polynomials are called atoms, it just means that I can't factor it in a non-trivial way without these two factors being invertible. So Cohn developed all this theory of factorization of matrices over free algebra, factorization in free algebra in general. So he proved that, yeah, okay, every NC polynomial you can always factorize it in irreducible factors. And how many factors there are going to be, that's unique. However, uniqueness is a bit problematic. I mean, it's not like in the commutative setting, right? I mean, commutative polynomials, it's a unique factorization domain. Here you have this kind of a stuff happening. So this polynomial factors in two ways that they don't look too similar. I mean, this polynomial here, x1, x2 plus 1, that's, I mean, it's not a scalar multiple of this polynomial, right? And this one is not a scalar multiple of this polynomial. So there's some non-uniqueness happening. So we kind of, we want to make up for that first, right? And we have this notion of stable association. Again, it's due to Cohn, or maybe even older. So if I take two polynomials, f and g, possibly of different size, then we say that they are stably associated if there exist invertible matrices over polynomials, such that, well, maybe I need to enlarge it in a trivial way. So this g plus identity just means that I put g, and then maybe I need to put some identities, ones here. So when I enlarge g a little bit, and I enlarge f a little bit, then you can go from one to the other just by multiplying with invertible matrices. So maybe, and that's really kind of unnecessary. So here we have this example from the, so we have this non-uniqueness of factorization. Here, look at this first factor and the last factor. You can check that they are stably associated, so that they are not associated, they are not, one is not a scalar multiple of each other, but once we enlarge them a little bit, we can find the invertible matrices. So they're invertible, such that they satisfy this relation. And again, going back to Cohn, so complete factorization of this type always exists, and it's actually unique up to stable association of irreducible factors. Right? Those factors, like in this example here, one can show that this factor is well, we just saw that these two factors are associated, but for example, also these two factors are associated. So once you impose this equivalence relation of being stably associated, factorizations they become unique. And also stable association, it's not hard to see, but it preserves irreducibility, right? I mean, if something is irreducible and something else is stably associated with, that other thing should also be irreducible. Now what's going to be especially important for us today is that if we have two stably associated polynomials and they satisfy a relation like that, then they will have the same singularities. Right? I mean, we see that from here. I mean, if I put some x's in here, well, that's always going to be invertible, that's always going to be invertible, so g of x is going to be singular if and only if f of x is going to be singular. So the point is, free loci definitely cannot distinguish between stably associated polynomials, right? So that's, they can't do that, but I mean, is that all there is? Maybe that's the question. Free loci are the same shit. Polynomials is stably associated. Now another thing why this stable association is important is that, and that goes back to Higman, so it comes from group theory that, well, the idea comes from group theory that every polynomial is stably associated to something linear. And that's, it's kind of, again, some analog of sure complement business if you want. And what's going to be important is also that, well, if this f, if I plug in zeros and I get some invertible matrix, well, then you can always choose L to be monic. So L of zeros again. Now, as I said, I mean, it's this getting this linear pencil. It's not hard, right? But this L is not unique. So what can happen is that you can always, in a really easy way, you can take your polynomial, you get a pencil out of it. However, that pencil might have a big size, related relative to the original size of f. And then it's kind of hard to work with if I want to form coefficient algebras and so on, like in the previous slides. So you want to do that efficiently. You want to kind of find the smallest possible L that does that. And at least in the monic case, well, the most efficient way to do that is by realizations of anti-rational functions. We've already seen some realizations in the last 2 days. Basically, there's different kinds of realizations. I mean, it depends which one's your favorite one. For the last year or two, for Marchesini one's my favorite one. So every rational functions, non-commutative rational functions that's defined at the origin can be written like that. So here, this is some constant matrix, so just the value of r at 0. C is going to be a control, C transpose is constant row. B is a linear vector in x1, x2, and so on. And L is a monic pencil. Now the important thing is getting minimal, if you give me a rational function R, and you want to find a realization like that, that's essentially linear. How to do that, how to find the minimal. And why is that important for us? Well, I mean, if you take a polynomial, NC polynomial, or matrix of it, such that at 0 it has an invertible value, then you take the realization for f inverse, so f inverse is a rational function, you take the realization for it, and then this L that I got from here, that's the L stably, that's an L stably associated f, it's optimal size. That's the machinery that kind of helps us go from polynomials to pencils. Now that we have this machinery, right? I mean, how does this machinery translate of? Well, I mean, if I start with something that's irreducible polynomial, what's the property, the corresponding property with pencils? Well, we don't call them irreducible pencils for some reason. I mean, and there's some reason, but they are what we call indecomposable pencils. So being irreducible essentially means that my pencil has coefficients a0, a1, so on, such that I can't find any invertible matrices. I can't change the basis in such a way that this would split in a block structure. I can't make like a big zero block here. That's what it means to be indecomposable. Like building blocks, you could think about it, well, I mean, you start with a pencil and then you start changing bases, and essentially what you're going to get is some, so these are going to be your building blocks of the smallest possible building blocks of all pencils. A little different, well, a little nicer situation is if this is a monic pencil, so if A0 is an identity matrix, then you don't need two matrices P and Q, but by this being monic, you actually just have one matrix and you just simultaneously, well, you just do the same basis change on both sides, and then you, again, being indecomposable means that there's no basis change such that you get this block decomposition. And maybe that's, yes?
So what is the size of this zero?
So the zero, so these should be square sizes. These should be square sizes. Okay.
So zero can be 1 by 1 also.
Well, I mean, if I want this, so if
okay.
A was a square matrix, then I want, yeah. So if this was delta times delta, I know if this is A times A, B times B, then this is B times A. Okay. And now the thing is, if K is algebraically closed field, so think of complex numbers, then saying that there's no P such that this can be put in this triangle, it's equivalent by Burnside's theorem that these tuples of A1 to AD, they generate the full matrix algebra. So these AJs were epsilon times epsilon size. Yeah, I know this Greek letters, maybe not the best notation, but so this thing is equivalent to they generating a full algebra. And that's, you see, this is much easier to check a priori than this, right? I mean, here it's kind of you're looking for common invariant subspace, that's annoying, right? And here, well, I'm just gonna start making products of matrices and check how big of a algebra they span, right? So that's probably the main reason why the monic situation is much better than the non-monic situation, because here you don't have some equivalent statement like that. You don't have equivalent Burnsides. Okay, and now at this point I should mention a little bit of invariant theory that, well, you saw that in this, that we talk about indecomposable pencils, we kind of talk about how matrices act on pencils, and so that brings some invariant theory in all these problems, and basically there's three types of actions that we care of. So first of all, on matrix points, right, I said at the beginning that free locus is invariant under simultaneous basis change. So that means GLN acts on tuples of matrices both simultaneous. Now a lot is known about this action, namely we know what are polynomial invariants due to Procesi, so they are all polynomials in traces of products and matrices. So these are called trace polynomials, or pure trace polynomials. And we know to generate all polynomial identities we actually just need those that have at most n squared matrices in here. So we kind of have that there are bounds and generators. There's also a lot known about relations, so like which these polynomials represent 0, and also again that there are some bounds, like that there's no relations of degree less than n plus 1, so relations won't start from some size on. And we also know what are, I mean, if I take point here and I take it for a round with the GL action, and you ask yourself, well, is this orbit closed or not? Well, it's known that, well, it's closed if this is kind of if the point gives me a semi-simple algebra, so it's basically direct sum of indecomposable ones. Anyway, the point is all this theory that what we know about these invariants, how they look like, bounds on generators and so on, that's going to come into play that's going to play in the question of what does it mean for free locus? So this is, I mean, if I fix some n, so the nth level of free locus, when is that an irreducible hypersurface? So in the analysis of this question, this group action is going to come in. And we have one more GL action here happening. So here GL was acting on the points that I'm going to plug in the polynomials, in the matrices. But you can also, like in the previous slide, GL also acts on the coefficients of monic pencils, right? And that's going to play in the question of well, if I have two monic pencils, and if their free loci are the same, does that tell me that L and M are in the same orbit, right? I mean, this question. So that was for monic one, and then in the non-monic case, we saw that, well, we need to have different matrices from different size, P and Q. So it's GL times GL action, so simultaneous left and right multiplication. For general pencils, you act on the coefficients. And again, here are again known results of what does it mean when is some point, when the sum point has a closed orbiter and trivial stabilizer and so on. And again, that's going to help us with the question of what does it mean if two pencils, if they have the free locus, does that mean that they are in the same orbit? Actually, here I should say, well, and these results are actually for SL times SL. But it's a pretty similar situation. Okay, let's look at some example here. So let's take this monic pencil, L, 3 times 3. You can check that it's indecomposable. Well, we just checked that these two matrices generate all 3 times 3 matrices. And you can also check it's stably associated to this quadratic polynomial. And then you check what happens when I plug in scalars. So the first level, I plug in 1 times 1 matrices. Well, this hypersurface is going to have 2 components. It's going to have 2 lines. So it's even though this was kind of a indecomposable, irreducible pencil, the first level it factors, right? I mean, I have 2 components. However, you can check that when I plug in 2 times 2 matrices, then you get something that's irreducible hypersurface in pairs of 2 times 2 matrices. And that's actually something that happens in general. So from now on, let K be an algebraically closed field. What happens is the following. If you give me an indecomposable pencil, then the free loci levels, they are going to be irreducible hypersurfaces for large enough n's. They might not be irreducible for all n's, that for some small n's things might go wrong. However, when n is large enough, again, what does large enough mean? We'll talk maybe at the end. But it's going to become irreducible. So so that means, I mean, relates to the fact that what I was saying at the beginning, we want to know what are the components of free loci. Well, if I have an indecomposable pencil, it's just going to have 1 component for the pencil. So there's a bit of a difference of a proof. Well, wait, I have 10 minutes. Okay, I'm going to say something about the monic case. So how do you prove that in the monic case? There's actually three steps. The first step is the most technical and annoying. Again, use algebraization trick. So you want to prove something like that. So if you know that this pencil, when I add one more variable at the end, if this pencil is irreducible for large enough n's, then this pencil is going to be irreducible for 2 times the size that I used before. So somehow you see that, if I know some irreducibility, if I add to my coefficient some of the products, then I can say something about irreducibility of the original pencil. And now remember that this L was indecomposable, so in the monic case that means that the coefficients of L degenerate the full algebra. Right? So now you're thinking, well, I want to show irreducibility of that. Okay, I can add one product and I'm showing the irreducibility of that, and you keep adding the products to your pencil. What's going to happen eventually, your products are going to span the whole algebra. So eventually you're going to get determinant of something that spans the whole algebra. So up to basis change, it's going to be just a determinant of a big generic matrix. And determinant is a polynomial, it's an irreducible one. And then you, using the first step, you roll back down that you see for large enough n's, this is going to be an irreducible hypersurface. Okay, there's a bit of a difference for the general case. You actually need to reduce it to the monic case. I still don't know how to prove the general case directly, but anyway, it's all sorted now. So, and then because, as I said, like stable association preserves irreducibility, one can actually prove that now. Okay, if you give me any polynomial that doesn't factor, then the free locus it's going to have only one component for large n's, large enough for most n's, for almost all n's. Okay. Now that we have irreducibility, we also can go on and start talking about what happens if the free loci are the same. So And there's a really nice answer if you have indecomposable pencils, so if you have these pencils that you can't reduce to triangular form, then two free loci are the same, even though if they are the pencils are actually of the same size and they're in the same orbit in the sense that, well, they're basically the same, just up to a basis change on left and right. And finally, we get a Singulärstellensatz, so a version of Nullstellensatz for singularities. Namely, if I take two full polynomials, again, what's full? Full just means that they don't factor in this trivial way. Then the singularities of f are contained in singularities of g, if and only if every factor of f it's more or less a factor of g, up to that equivalence relation that we need to take into account, because you can't live without it. So we kind of, we get like, well, I guess as good as it gets when it comes to answer.
So, so you cannot still test if non-commutative polynomial is irreducible, right? Because you need a bound of that n. Like even randomized, because you're doubling all the time, or do you have an algorithm?
No, so yeah, checking how a polynomial, if a polynomial is irreducible or not. We have an algorithm if I take, if I really take an NC polynomial in the sense that I take delta equals 1, so really element of the free algebra, and I need to assume that it's invertible at 0, that it's non-zero at 0 when I plug in origin.
But that you can assume by shifting everything. Right?
Well, okay, and yeah, that's also true, yeah. But then, for example, you take a commutator. Commutator you can't shift into a scalar point when it's invertible, right? So those are a little bit problematic. However, if you're in some nice situation that at least at some scalar point it's going to be non-zero, then with realization theory actually gives you probabilistic past linear algebra, probabilistic algorithm how to check if it's irreducible or not.
So for delta equals 1, you can do polynomial time. But
yes.
Can you prove that this n is also polynomial for delta equals to 1, or?
No.
Right. No.
No.
Ah. Okay.
But that's possibly just my inability than an actual fact, yes. How much time do I have? 5 minutes?
Yeah, 5 to 10.
Okay. Yeah, I'll say a few more things about this n at the end. Yeah, we'll come back to that. Okay, so this was kind of a, okay, this is all nice and neat, but this is kind of a, if you want, that's a complex situation. As I said, I'm thinking here of case algebraically closed, right? I'm thinking of complex polynomials, complex matrices. How's that going to tie in with the, let's say, positivity domains that we heard about? They kind of need some real structure, right? So, okay, let's now also add another set of variables, which I'm going to call x stars. These are going to be formal adjoints of the variables x. And now if I have a polynomial that has variables from x and x star, I'm going to assign to its real free locus. So these are going to be all tuples of matrices x such that f of x, x star is singular. And this is kind of a real setting because you can think of it like if instead of this x star I would be plugging in y, these are kind of, I think of them as complex points versus the real points x, x star. Think of it like ZZ bar and, yeah, well, ZZ bar and so on, right? Yeah. Okay, so, and that's the thing what I was describing at the beginning. So if I have a Hermitian polynomial in x and x star, I mean, that describes the semi-algebraic set that Igor and Scott were talking about. And then, yeah, this real locus, so points x such that f of x, x star is singular, that's really more or less a real Zariski closure of the problem. So these are actually then so the real free locus is what we care about when we talk about convexity and positive Stellensatz and so on. So how does the theory before, when we were kind of involution free without any stars, how does now that theory translates into this setting? Well, to some degree it does, right? So first of all, whenever I see a polynomial x and I treat it as a polynomial in x and x star, I'm going to call it analytic because it has no x stars. And then another kind of polynomials are going to be the Hermitian ones that are unsignatured in the sense that they will change the sign. What does that mean? Well, I'm going to find some n and two matrix tuples x and y, such that f of x and f of y have different signature, different amount of positive and negative eigenvalues. for example, every Hermitian-monic pencil is like that. And then we have this kind of theorem, so we kind of have good Nullstellensatz for these types of polynomials. So if I take f analytic and g arbitrary polynomial in x and x star, then real singularities of f are contained in real singularities of g, if and only if either f or f star is basically a factor of g. And the other type is, well, this unsignatured thing, so if I have an f that, morally speaking, changes sign eventually, then again, the inclusion of real singularities of f in the real singularities of g, it basically means that f is going to be associated with f of g. So these are two settings where we can have a real Nullstellensatz.
So 2 is really similar to the usual commutative real Nullstellensatz, right?
Say that again.
So 2 is really the similar one to the commutative real Nullstellensatz.
The point is kind of
if the polynomial changes signs, then
means that real points are going to be dense in complex points. Yeah, that's exactly what you prove. And this is the first setting. Yeah, also it's also essentially in some sense reduction to that somewhere there's going to be enough real points in some sense on some variety. Yeah. Okay, I'm going to skip that because or maybe not.
At least 5 more.
Oh, okay. Then let's talk also about this. So that was about real points. Then there's also something about smooth points if you want to explore this geometry of free loci a bit more. So let's fix a polynomial. And now, okay, free locus is the points where f of x is singular. And now let's be a bit more precise. Let's look at those points where f of x is singular but not too singular. So the kernel is one-dimensional. And so this kind of means that 0 is, well, eigenvalue with geometric multiplicity 1. And then, well, you also want to say something about algebraic multiplicity. So what does it mean that f of x has algebraic multiplicity 1? Well, it's this condition here. So we look at this kind of simple points in some way. The dimension of the kernel is non-zero, but it's small. And then you can check that if f is an irreducible polynomial, then again, at least for large enough n's, between these two sets of this points where kernel is dimension 1 and kernel is dimension kind of 1, these two sets can be different, but what's in between is the smooth points of the free locus. Smooth points lie in between. And why is that important? Well, I mean, if you're doing something in the Hermitian setting, so for positivity domains and so on, then when things are Hermitian, then geometric multiplicity and algebraic multiplicity, that's the same thing, right? So I mean, in that case, at least these two things are the same. So kind of a smooth points can be described like that. So if I have an irreducible Hermitian pencil, then for large enough n's, x0 is a smooth point on the boundary if and only the dimension of the kernel is exactly 1. And again, that only holds for large enough n's. So for example, there was Kippenham's conjecture essentially said that, oh, n1 should work all the time, and that was in 51. And the answer is no. I mean, you need to go high enough. It's not going to work from the. So, and there was a counterexample by Laffey when he took some pencil of size 8 times 8. And why is this important? So why is it important that smooth points correspond to points where kernel is one-dimensional? That was kind of that kind of comes into play when you're talking about bianalytic maps in complex sets. So this kernel one business is super helpful. Okay, now let me just say a few things about what are open questions. As Raphael said, I mean, yeah. There are a few problems. I mean, there are some problems here about polynomial bounds on testing this inclusion of free loci. So the thing is, we know that if you give me two pencils A and B, if I want to check the inclusion of free loci, I just need to check it for finitely many n's. However, the current bound on how big n do I need to take, it's exponential in size of A and B. And also, if I have an indecomposable pencil, how high do I need to go such that this becomes an irreducible hypersurface? Again, I know that it's okay if I go exponentially high corresponding to the size of L. However, in practice, it doesn't look like that. N should be much lower. this exponential size really comes from the way how we proved stuff. If you remember, I said one of the main things here is the algebraization trick, and then whenever you want to take into account of a product, you're doubling the size of matrices, so that's where you get this exponential growth. However, we would hope that maybe with some advanced invariant theory, one could get some nicer bounds. Right? There's also a question, I mean, okay, this free loci actually, they've proven super useful. I mean, is there some intrinsic definition? So, I mean, what's a free loci? It's a family of hypersurfaces. They are invariant, their degrees, they grow linearly with the n, and they have some compatibility property between different levels. Is that actually suffice to say that, oh, this is really a free locus of sometimes if you give this axiom? And there's some questions related to, so I said, well, smooth points correspond to so smooth points correspond to x, where f of x has kernel 1. Now, the other side that's kind of interesting also from the convexity point of view is like, well, but what about those points where f of x has high kernel? So kind of I would like to find some reasonable bound on n, so that I would like to know that, oh, if I go high enough, if I put high enough n, I'm going to find some point x where f of x is going to have sufficiently large kernel. That's again, I don't really have a reasonable bound for that. And finally, I mean, this real setting, when we look at the real free locus, as I said, we have some answers for analytic polynomials and for unsignatured polynomials. The question would be, okay, something can be done for general f and g, I mean, maybe some SOS techniques. And of course, the test case would be, I mean, can we characterize polynomials that they don't have? The real free locus is empty. We don't actually good answer to that. Okay, and I guess that's a good place to stop. Thank you.
Questions? Questions? Oh, sorry.
Yeah, so I guess in the last point you're looking for something like rare, non-commutative real radical.
Yes.
Condition. Yeah. And maybe regarding the second point.
Just one more thing before. Yeah, and it's kind of interesting, right? I mean, the complex setting that kind of corresponds to factorization, right? And real radical, I mean, there should be some sum of squares. I just don't know how to put that.
So there are
How you would do compatibility between these two, like SOS certificates versus factorization certificates. I don't know how that's gonna glue together. Yeah, sorry.
Yeah, no, regarding the second point, I just wanted to make a comment that this is probably related somehow to another question that we don't know an answer to, namely how to characterize non-commutative rational functions in terms of their evaluation. So if we have a non-commutative polynomial, and if we evaluate it on n by n matrices for all n, then we'll get something which is polynomial in matrix entries. And conversely, if we have a function which is defined at all levels, which is polynomial in matrix entries at every level, and which satisfies natural compatibility conditions, then as soon as the degrees are bounded, we know that it comes from non-commutative polynomial.
And an equivalent here for
somehow a
functions.
conjecture along similar lines would be that if in the rational case, if we have something that whose degrees grows at most linearly in n, it would come from a non-commutative rational function.
Yes, yeah, exactly. That's.
Other questions? Just thank the speaker again. That does it for the morning.
Yeah, you're off the hook. Thank you.